All right, we're looking at the back page of the Chapter 3 Morning Review. Again, we're looking at a derivative graph for this problem here. The derivative f has 0 at x equals a and a relative maximum at x equals b. Okay. Which of the following is not true? So I'm just going to go ahead and create characteristics or identify some characteristics of this derivative graph. Again, we know that any parts of the graph that sits above the x-axis is going to be where the slope is positive. Any parts of the graph that sits below the x-axis would be indicating where the slope of the original graph is negative. And we also know that at b there is a relative max. So any peaks and valleys of our f prime graph will represent where points of inflection is. So we know the original graph will have this behavior where to the left of a, the graph is below the x-axis. So we know the original graph will have a negative slope. And then to the right of a, all this is above the x-axis. So we know the original graph will have will be increasing. So just based off of some general observations, we know that the original graph will decrease, hit a minimum of at a, and then increase again. Okay. We also know behavior of concavity. We know to the right of b, the graph, the f prime is increasing. So wherever the f prime is increasing, that will indicate where the original graph is concave up. So concave up all the way to point B, and then to the right of B, concave down, because the slope becomes negative. So we know this behavior. Now let's look at some options here. F of x has a relative minimum at x equals a. We know that's true. Decreases, hits a relative min, increase again. F of x has an absolute max at x equals b. Well, it is the absolute max of the f prime graph, but it's not going to be the absolute maximum of the original graph, because we know that from point B, the graph is going to increase, but it'll resemble concave down graph. So increase, concave down, that doesn't necessarily mean that the graph is going to stop increasing. The graph is still going to continue increasing, because the slope will still be positive at that point. So this is false. Let's look at some other options, even though we know b is the answer. F of x is increasing on the interval from a to b. From a to b, we know the graph is increasing because that portion is above the x-axis. That's true. F double prime is positive from a to b. So from a to b, f double prime is positive. Yes, because concave up. Okay, concave up all the way to b. And f double prime has a 0 at x equals b. That is also true. F double prime is equal to 0 because the slope of the f prime graph is 0. Okay, number 6, which of the following statements are true about the graph of f? So let's look at some behavior here. F prime is greater than or equal to 0 on the interval from d to f. So from d to f, f prime is going to be positive, which is true. From d to f, simply because the slope is positive here. F double prime is equal to 0 on points b, d, and f. F double prime is equal to 0 at b, d, and f. So here's b. Okay, here's d and here's f. That is going to be false, because that's where f prime is equal to 0, but not f double prime. Okay, f double prime is greater than 0 on the interval from a to b. So from a to b, f double prime is positive. We know that's false because we're looking at the f of an x graph, not f double prime. F double prime is greater than 0 on the interval from d to f. So from d to f, we know this is also false because the graph changes from concave up to concave down in that interval. So it's not always going to be positive. So the only thing that's true is just going to be the first statement. Hey, number 7, find the extrema of the function. So we want to find the absolute max and absolute min of a polynomial on the open interval. So to find, that means there's no endpoints to have to test. We just have to look at critical points and determine whether the critical points will be enough to determine whether there's any relative max or absolute max, or relative extrema or absolute extrema. So to find the critical points, we need to find the derivative. So we can go through power rule, bring down the 3. The 3 and 1/3 cancels out, so x squared minus 12x plus 35. 35x becomes 35, and negative 1 goes to 0. We set our derivative equal to 0, find our critical points, which is at 5 and 7, and then we test values in each interval with the f prime graph. So here, if I plug in 4, I get negative times negative, which is positive. If I plug in 6 here, I get negative times positive, which is negative. If I plug in 8 here, I get positive times positive, which is positive. So we expect a relative max at 5 and a relative min at 7. However, the graph is continually increasing. So the graph will go down to negative infinity, and the graph will continue up to positive infinity. So we know that these points cannot be absolute max or absolute min, because the graph is going to negative infinity on one side and positive infinity on the other side. However, we do know that there is enough information to confirm that these are relative max and min. So we know at x equals 5 they're a relative max because slope changes from positive to negative. We know at 7 there's a relative min. Slope changes from negative to positive. Okay. Find all the critical points in this function here. So critical points means that we just find the derivative and set equal to 0. So again, we go through power rule for each of these terms. This becomes 2x squared. 5x squared becomes 10x. Negative 28x becomes negative 28. 10 goes to 0. We set our derivative equal to 0. We can factor out the 2, factor out the remaining expression. Solve for x. We get negative 7 and 2. Okay, number 9, find the inflection points. So to find the inflection points, we need to work our way down to the second derivative function, and then test and confirm with the critical points. So we need to first get to f prime. So to get to f prime, I'm going to go through product and chain rule here. So 2x and x plus 4 cubed, these are two separate expressions that are related to one another by multiplication. So we go through product rule first. So f prime g, so f prime, 2x becomes 2, g is x plus 4 cubed, plus fg prime, so the f is 2x and g prime is 3, x plus 4 squared times the inside function's derivative, which is 1. From here, to make things a little bit easier, I'm going to just try and clean this up a bit. So the expression to the left and to the right of the plus sign, I noticed that there's common expression that I can pull as a common factor. So I can pull x plus 4 squared out. I can also pull 2 out. And then if I take this from both terms, I'm left with the first expression left with x plus 4, and the second expression I'm left with 3x. Combine those like terms, I get 4x plus 4. So now I have a cleaned up version of f prime. From here I can go to f double prime. Actually, I'm going to combine the 2 with the 4x plus 4. So here is the cleaned up version of the f prime. Now I'm going to work my way down to f double prime. Again, we're going to go through product rule, and within product rule we'll go through chain rule. So f prime g, so f prime x plus 4 squared becomes 2x plus 4 times g, so that's the original 8x plus 8, plus f, so that's x plus 4 squared times g prime. 8x plus 8 becomes 8 because 8x goes to 8 and 8 goes to 0. So now this is my f double prime. I'm going to continue to factor this. On either side of the plus sign, I'm going to factor out an x plus 4 and an 8. I can also pull an 8 from this expression. So if I pull an 8 and x plus 4, the remaining expression is 2 times x plus 1. And the second expression, I'm left with x plus 4. If I combine those terms together, I get 2x plus 2 plus x plus 4, which is 3x plus 6. Now this is the nicely cleaned up version of f double prime, which we can now pull, we can now set equal to 0 to find our critical points. So x plus 4 goes to negative 4, 3x plus 6 goes to negative 2, and then we have to also make sure we test those critical points by confirming that there's a change in sign on either side. So to the left of negative 4, if I plug in negative 5, I'm going to get a positive value. If I plug in negative 3 for this interval, I'll get a negative value. And then to the right of negative 2, if I plug in 0, for instance, I will get a positive. So there's a change in signs at each of those intervals. So we know there's critical points, points of inflection at negative 4 and at negative 2. And then if we're asked to find the inflection points, we also need to find the y values. We plug -4 back into the original function, I'll get 0. So order pair at -4, 0. If I plug -2 into the original function, we'll get -32. So the points of inflections are at -4, 0, and -2, -32.